What's up, everyone? We're live for night 4 or day 4 of the AP Calculus ABBC review. And for this one, I'm going to do things a little bit different. I'm just going to speed through the 10 units to talk about big ideas, and then I will go through 20 multiple choice questions. I do apologize. I did tell people yesterday that I was going to start at 3:30, but I did send out a message saying, family issues had popped up. So yeah, that's why I'm starting late. Actually, I'll yeah, it was just something family related where I was gonna drop my kids off, and something came up that I just was not able to drop them off, um, to be watched. So I'm a dad first, and I'm a YouTuber second, but yeah, everything will be all good though. So now this will have to do. But I do appreciate you all for, being patient and being here. 71 of you here at the start is like pretty awesome. So I'm happy to have you all here. Yeah, thank you. I'm doing fine. It was actually my dad. He's okay, but his pet had passed away. His dog just like out of nowhere got sick. Was an older dog, and just got sick, and the dog died. So I was like it was just a bit of a sad day, but I am gonna keep to the review and stuff, and yeah, that's what will happen. So all right, now I am looking at the exam weight for A, B, and BC. One thing I want to point out here is, I mean, it's fairly late in the game. It's the night before the test. But in terms of what to be good at for tomorrow, the most important stuff to be good at, I would say here, are these units. Okay, these are the big units for the AP test. Like if I had to prioritize for each exam, like what I want to show up good at, it's these units here. I'm not saying like, oh, let's just fall asleep with limits, but like those are the heavy hitters. Okay, so you play the numbers game. If you're not the best at squeeze theorem, that is not going to wreck your score. Okay, but if you aren't good at the fundamental theorem of calculus, like yeah, that's going to hurt your score quite a lot. It's pretty interesting. Like the most valuable portion of the test is from unit 6. So I think people kind of may already know this, but just in case you don't know that, this is what's happening. All right, so let's get rolling here. So I just want to talk units 1 through 10, big ideas, and then I am going to do multiple choice 20 questions to cap it off. But I had put out a survey recently saying like, oh, which part of math do you struggle with the most? And the top vote was the concepts. So I thought, I figured, let me try something a little bit different. And for this, when does a limit exist? So I'm talking unit 1. And for this, I think of two cases of when a limit exists. I could have a situation where I'm looking at a point on the graph where the function is continuous. So let's say here I have a situation like this, and let's say this is located at, I don't know, 1, 4. And then I go over here to -1, and I'm going to put an open circle here and a 2 here. So in both of these cases, I could say, well, the limit as x approaches -1, and let's call this f of x, the limit exists, it's equal to -2. Because as I approach from the left and right side, I'm heading towards a specific value. But if I look at, let's say, the more obvious case is when your function is continuous. Let's say I find the limit as x approaches 1, I'm going to get 4. So this is just concept here. And yeah, some concepts like for you to hang on to. What does it look like when the limit doesn't exist? So what you want to be on the lookout for is situations like this, where you have a jump in the graph like this, or let's say you have, let me make that neater. So let's say we have something like this. Okay, we have an asymptote. Okay, so in a situation like this, let's say this is happening at 1, and let's say this is 1, this is 2. The limit as x approaches 1 of g of x, I'll call this, does not exist. And why? Because the left side limit of g of x if I approach g of x, I'm sorry, if I approach 1 from the left, so let's say I'm approaching from the left side like this, I'm heading up to 2. But if I approach g of x from the right side, I'm sorry, if I approach 1 from the right side for the graph of g of x, now we look here, and approaching from the right sends us down to 1. And since these limits are not equal, the limit does not exist. So if I had to say why here, like why does the limit not exist? I could say because, and then I'll just include this here, because the limit as x approaches 1 on the left of g does not equal the limit as x approaches 1 on the right of g of x. Okay, so the left and right side limits have to be equal. So a jump discontinuity is one case where the limit doesn't exist. And then the next case, let's say this is at x equals 5, is a vertical asymptote. If I have the limit as x approaches 5 of g of x, and let's say I'm approaching from the left, notice that we're heading up to infinity. Okay, so right away, if my limit is infinite, that means the limit does not exist. I mean, sometimes they'll ask you for a direction like this. On the left side, we're going to infinity. On the right side, we're going to minus infinity. Okay, but what is continuity? So I'm not going to go through every single topic from unit 1, just the biggest topics. And I am definitely, I will go over Lagrange. I have that at the end of unit 10. So I will talk about Lagrange for sure. So here I have, in third grade language, a function is continuous if you could draw it without lifting your pen off the page. Okay, but if you write that as an explanation for the free response, they're not going to give that credit. The textbook definition that you have to know is the limit as x approaches c of f of x equals f of c. Okay, if this is true, then f is continuous at x equals c. All right, so this is a very, 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 very important definition to know. Okay, in terms of unit 1, like this is like one of the really important ones. Okay, so just make sure, especially this part here, that you know this, that if this limit is true, the function is continuous. If I just make up an example on the spot, let's say I have f of x equals, so something like this, x squared minus 9, this is a popular one, over x minus 3 when x is not equal to 3, and then when x is equal to 3, it's 6. So something like this, if I go through the definition, oh, whoops. Let me just, because I'm on that magic pen. Sorry about that. So this, let's say here, I take the limit as x approaches 3 of f of x. The limit as x approaches 3, I could do L'Hopital's rule, but I'll just go ahead and do algebra here. So I have this. The x minus 3's cancel. 3 plus 3 is equal to 6. And now I could find the function value at 3. The function value at 3 is also 6. So then if this were the free response, FRQ, more likely for the calc AB people, but BC, they can ask you to use this definition. If they wanted you to explain why f is continuous at x equals 3, you would say, since the limit as x approaches 3 of f of x equals f of 3, f of x is continuous, okay, at x equals 3. So me, when I have trouble remembering a definition, word for word, I think of the picture. And if you look here, let's say I call this L. The limit as x approaches c, I'm approaching c left and right, and see how I'm heading to L. But that's also my function value here. Like if I say my x is c, my y value here is L. So that's how I see continuity in my head, is I just see a picture. Okay, so, all right, cool. So let's move on. Asymptotes. So limit definition for asymptotes. So let's say here I look at a horizontal asymptote. So something like this, or maybe it's this way. So for this one, I could have a function that looks something like this. Actually, let me draw that a little nicer. I'll bring these a little closer, just so it's easier to draw. Okay, so if I had something like this, Or I could have something like this. And let's say I call this C1 and C2. Okay, I'm just going to name those. If you forget the definition for an asymptote, like that y equals C2 is a horizontal asymptote, I'm just going to abbreviate. And then y equals C1 is also a horizontal asymptote. Just think about the picture. If you look at the picture, the limit, let's say I call this function f of x, the limit as x approaches infinity of f of x, as I go to infinity, see how this is heading up to C2. So since this tells us that y equals C sub 2 is a horizontal asymptote. Okay, so when you're looking for a horizontal asymptote, you're taking the limit as x approaches infinity. However, you also have to check the limit as x approaches minus infinity. Okay, a lot of people, when they mess this up, they forget to check minus. And if I go this way, I have a different asymptote. So y equals C1 is a horizontal asymptote. I'll think of an easy function, like think of e to the x. Looks like this. Okay, the limit as x goes to infinity of e to the x is infinity. This goes to infinity. However, if I go backwards to minus infinity, now my limit is 0. So the x-axis, or y equals 0, is a horizontal asymptote of e to the x. So I just talking you through concepts, like why does this work? Just imagine what it looks like. Okay, so this is, I'm just speeding through the big ideas. All right, and for a vertical asymptote, it's one of two possibilities. It's the other way around. If the limit as, let's say I call this C1, I'll call this g of x. Let's say I have the limit as x approaches C1 on either side, like let's say the left side, but in this case, the way I drew it, left side of g of x. If that goes to plus or minus infinity, in this case, it goes to plus infinity. So since this x equals C1 is a vertical asymptote. Okay, I could also have it where I approach on the right side here. And when I approach on the right side, I go to minus infinity, and that's also fine. IVT. Okay, IVT, true story. In 1999, I was 5 feet tall. Okay, so I was 5 feet tall. Today, in 2024, unless I shrunk, I am 6 feet tall. So the concept, I always ask my students, is it possible, could I have skipped 5'4"? Okay, is that possible? And most of them say, no way, because 5'4" is between. So that is the $1 million concept here. So for one, I have to verify f is continuous. And here, they're going to tell you that f is differentiable or something of that sort. And f here is a polynomial, so I could say, yeah, f is continuous here. I'll say f of x is continuous. They're not going to make you write like a, 10-page story as to why. But I could just say f of x is continuous. And I could just, how about I'll add a because f of x is a polynomial. Okay, so I'll just sprinkle that in. But that's really, going extra here. And I don't know what just happened. Okay, we move that up. And let's try that again. All right, is a polynomial. All right, now I find the function values at the endpoint. So f of 0 is equal to -1, and then f of 3 is equal to 27 minus 24 minus 1, which is going to give us 2. Okay, if people want to fact check that, 27 minus 24 is 3, minus 1 is 2. Cool. So then we have to think here. 5 foot versus 6 foot. Okay, -1 versus 2, that the function has a root. A root is where the function is equal to 0. So the thought process here is that we have a function. At 0, we're down here at -1. And at 3, we're all the way up here at 2. So no matter what this thing looks like, it is impossible for us to skip the x-axis. On our way from -1 to 2, we have to pass through 0 at some point. Okay, like that's the concept. So then I just have to communicate that. I have to verify that the value is between the two endpoints. So here I would say since -1 is, and I'll write it in function language. I'll say since f of 0, which is -1, is less than 0, which is less than f of 3, which is 2, by the intermediate value theorem, we'll say there exists a value c. C is going to be between 0 and 3. C is located on the x-axis. C is the location where the function goes to 0. So that's between 0 and 3 on the interval. Such that, and then I have f of c equals 0. Okay, that's us applying IVT and getting full credit. Oh, one thing to point out, that symbol means there exists. Okay, so that's IVT. And that is unit 1, right? What is a derivative? The concept of a derivative. If I have a function f of x and I draw something like this, the derivative tells you the slope of the tangent. Okay, so in terms of the definitions of the derivative, there's one fancy one. And let's say I call this point x, and I call this point over here x plus h. Now, the concept is, let me just draw them separate, is that here, if I find the slope between these 2 points, so let's say I find the slope between this one and this one like this, that's going to give me an approximation of the slope of the green line. And the slope of this one here is going to be f of x plus h minus f of x over, and if I take the difference here, x plus h minus x is just equal to h. So this is the slope of the secant line. But how do I make them exact? Well, I would move this closer. And as I move this closer, as I move x plus h closer, like h is shrinking, that moves the red point closer. And then this tangent line and this secant line, their slopes start to line up more and more. So my derivative, the slope of my tangent line, I could find by taking the slope of the secant line, which is here, and squeezing the distance between x and x plus h to 0. Okay, so that's the concept of what's actually happening here. The other formula is if I call this a, and I want the slope of this tangent line, so f prime of a, what I could do is I could just say, all right, well, let me call this point over here x. And it's the same concept, the idea of finding the slope between these two. But this time around, I'm doing f of x minus f of a over x minus a, and I'm taking the limit as x approaches a. If this limit exists, you could say then f is differentiable at x equals a. All right, I'm not going to sit here and just do 10 power rules and chain rules at you. I wanted to talk theory, okay? So that's just a big idea. Oh, I'm glad that you, that you were able to watch the replays and stuff. Yeah, I do. Once again, 613 people stopping by, and we're not even 20 minutes in. That's just truly awesome. I'm really I do appreciate you all. So many people have subscribed in the last few days. It's just really cool. So thank you. And if you haven't subscribed yet and you're finding this helpful, I would appreciate you joining the crew. So average rate of change versus instantaneous rate of change. Something I just talked about, but it's going to segue to eventually the mean value theorem. Okay, maybe I'll move this one actually after. Whoops. Oh no. The universe just imploded. All right, hang on a sec. Press the wrong button. Oh, good. It didn't fly too far away. Let me try that again without. Oh, well, this time it worked. That was nuts. Sorry about that. Okay, so average rate of change versus instantaneous rate of change. And you know what? I'll just throw it all on here because it's going to build into the mean value theorem. This is one of the big theorems for the test. Okay, so here, if I'm between a and b, and I have f of x, so there's f of x. what I want to look at is the slope of the secant line, which is going to be the line that connects these two. Okay, so here like this. And I'll just extend this out. Okay, and then I'm going to clone this. And I'll change the color of this one. So we'll make that one, we'll make it blue. So this is our tangent line. And the concept behind this, I always like to draw these out just so I understand what's happening, is that in black, what we have is this is the secant line. This is the average rate of change, which is over here. The average rate of change of f from a to b is f of b minus f of a over b minus a. The piece over here, this is the instantaneous, which is not easy to spell. Instantaneous, like this. Okay, rate of change. And for this one, it's right at one point on the curve like this. But notice these represent my slopes, the slope of my secant line and the slope of my tangent line. And from geometry, when are lines parallel? When they have equal slopes. So that's what I'm seeing here, is that's the location of our value C. Now, one thing you want to do when you're really trying to understand a theorem is challenge the conditions. F has to be continuous on the closed and differentiable on the open. So let's think about, why is that a requirement? Well, think of a function that contradicts that. Let's say f of x equals absolute value x. So if I were to look at this function, okay, absolute value x, and let's say I'm on the interval from -1 to 2. If I find the average rate of change on -1, 2, I would do f of 2 minus f of -1 over 2 minus negative. And this would give me absolute value of 2 is 2, minus absolute value of -1 is 1, over 2 minus minus 1 is 3, and that gives me 1/3. But looking at this, let's say I'm here at -1, 1, and I'm over here at 2, 2. I'm like, oh no, the mean value theorem lied to me. It told me that the average rate of change at some point will be equal to the instantaneous rate of change. But here, all along this, I'll call that M1, the slope is -1. And all along this piece, the slope is +1. So how come I'll never get a slope of 1/3? And the reason is that f equals absolute value x. Absolute value x is not differentiable at x equals 0. So it's not differentiable at x equals 0. And 0 is between -1 and 2. So MVT does not apply. Okay, so just, you really want to think about why the theorem has the conditions that it has. Like, why does the function have to be differentiable? Because that'll guarantee a smooth transition. So sometimes, like, they'll just say, like, oh, which of the following functions does MVT not guarantee a value C such that blah, 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 all this. And then you just have to check to see which one is not differentiable within, like, the interval they are talking about. Okay, so that's just something to throw out there. All right. So now, tangent line approximation. So this is another popular idea. And for BC people, your version would be the Euler's method. But let's say I look at the function, I'll call it g of x equals square root x. And I am going to look at 49. And the point over here is 7, okay? And that's because g of 49 equals the square root of 49, which is equal to 7. And for this, if I want to approximate the value of square root 50, I would write the equation of a tangent line here at this point and say, well, I don't know what the square root of 50 is, but I could plug into my tangent line, and that'll give me something here. Just by drawing it out, it'll give me something a little bit over what it actually is. So in order to get the equation of my tangent line, I would have to derive I would have the derivative of radical x, which is also x to the half, is 1/2 x to the negative half. So then I would have g prime of 49 is equal to, I'm going to call that 1/2 square root 49. And the square root of 49 is 7. 7 times 2 is 14. So this is the slope of my tangent line. So now this is my thought process. My slope is 1/14. My tangent line, the point that I'm using, is 49, 7. And now I just write the equation of the line. I have y minus 7 equals slope times x minus 49. Okay, so then y equals 1/14, x minus 49, plus 7. So the value of square root 50, which is, if I use the original function here, this is g of 50. Okay, g of 50 is square root 50. That is roughly 1/14 times 50 minus 49 plus 7. So this is 7 plus a 14th, or 5th grade language, 7 and 1/14. Okay, so this is the approximation for square root of 50. All right, that is, yeah, what we would do. So that's the concept, though, is that we're writing the equation of a tangent line and getting an approximation. Okay, so the approximation is on the tangent line. The actual value is on the curve. Okay, that's g of 50. Alrighty, so that is that part. Extreme value theorem. So the extreme value theorem is another big theorem. That if f of x is continuous on AB, then f of c is the absolute minimum or maximum on, okay, I'm sorry, and f of c is the absolute min or max value on this, then c is either a critical point or one of the endpoints of, or one of the endpoints, A or B. I'll just clean that up a little bit. One of the endpoints A or B. Okay. So what that means in pictures, because you're like, oh no, I might forget that, is if I draw something continuous on AB, then I have A and B here. And let's say I draw something like this. Draw that a little neater. It is obvious the way that we drew it, that like, oh, the absolute maximum is here, and the absolute minimum is here, and the other endpoint is here. But then people might say, like, this is a critical point. Like if I call this like C1 and C2, notice the way that I drew it, that the slope at C1 is equal to 0. And also the slope at C2 is equal to 0. So my highest and lowest point on a closed interval can happen at the critical points where the slope is 0. However, that is dangerous thinking, though, to say that that's going to happen every time, because one of the most common mistakes is that students don't bother to check the endpoints. So like, let's say I had a graph that looks like this. The person that just finds the critical points and says, all right, here's critical point 1, critical point 2, and they're like, that's the highest point and that's the lowest point. If you don't check A and B, you run the risk of falling in this trap of missing the absolute max and the absolute min. Okay, so when I hear the extreme value theorem, like, this is what I visualize. This is the sneaky case. Okay, the sneaky case is where the endpoints give you the max and the min. Okay, so just know your big theorems. Alrighty. First derivative test. This one is also massive. Okay, make sure you know this. So the first derivative test, if I have f of x, and I'm just going to draw something like this. So let's just see. So I have this and this. You know what? I'll even draw the sneaky case over here, which would have applied to the last slide too. I could have something like this as well. Okay, so let's say I have this, that if f prime changes from positive to negative at c, then f of c is a local maximum. Well, this I think is obvious is a local max because it makes a hill. But I want you to pay attention to the slope. The slope right before the hill is positive, then it goes to 0, and then it goes negative. So if you forget this, just imagine what it looks like or draw it out, and you're like, oh, the slope is changing from positive to 0 to negative. So that's, oh yeah, I'm going to do BC topics also. Yeah, so BC is coming. All right, so this is, once again, the concept. This is if you forget. And then notice down here, it's clear that I have a local minimum. And at this local minimum here, we have a slope that's negative, 0, and then positive. Okay, so if you do forget, that's how you're going to remember. Now over here, this is a local max, but it's the sneaky kind. Okay, it's the sharp turn kind. Just know that a critical point, to point out, there's two kinds, where f prime is 0 or where f prime does not exist. And C is in the domain of f. Okay, this one is the sneakiest critical point there is. When you have a sharp turn, it could still make a local max, and notice we still have that slope change from positive to negative. Okay, and then here I have a slope change from negative to positive at my local minimum. Right, but the idea is, if we had to do this algebraically, we have a function, we derive, we make a sign chart, and we're looking for the sign changes. All right, I will be doing multiple choice questions to like highlight these ideas for the second part of this stream, but that's the idea. All right, so cool. Moving on. Derive, yeah, I'm going to derive like when I do the actual questions. Right now, I just want to focus on the big ideas. So yeah, that's what I will do. All righty. So, all right. Oh yeah, this I'm going to go over on the actual thing that just stayed stuck there. So a second derivative. If I have f of x and I draw something, let me draw a little neater. Something like this. And I look, this part of the graph over here is concave down. Concave down. And this is where f double prime is less than 0. And then this part of the graph over here, the way I drew it, is concave up where f double prime is positive. What's actually happening is that f prime, the slope, is increasing. Okay, so over here, f prime is increasing. The slopes are becoming less negative and then becoming increasingly more positive. Whereas like over here, I have positive slope, and then it starts to flatten out. The slope is decreasing. Okay, so f prime, the slope, is decreasing. So just make sure you know all those big ideas. And where the concavity changes is the point of inflection. Okay, so this is a point of inflection when the second derivative changes signs. Okay, so just some big ideas. Now, one thing I like about drawing this out is there's like occasionally questions where they say, oh, I use the tangent line approximation. And I'm sorry, well, I'll say that for Riemann sums when we talk about Riemann sums. But when we do a trapezoid sum, if the curve is concave down, our trapezoids go under. Okay, and if I do a trapezoid sum on a concave up curve, the trapezoids over approximate. So it's also useful for talking about over under approximation, which now here we are, Riemann sum. So a Riemann sum, the whole point is to establish the idea of the definite integral. So let me just get this set up. So the definite integral, if I have something like this from A to B, is going to tell us the area under the curve. Okay, from A to B. So then this is now the integration chapter. The integral from A to B of f of x. I'm just checking this. Yeah, I'm making okay time here. This is exactly like, yeah, how much I wanted to cover. But this represents the space that I have over here. So the concept of the Riemann sum So let me just do this. Group and copy. Okay, now I'll delete this. Paste. Cool. Is if I want to approximate this area, let's say I want to do a Riemann sum with 4 subintervals. And let's say I do a right Riemann sum with 4 subintervals like this, equal spacing, is I'm cutting this into rectangles and finding the area of the 4 rectangles to get the area of the whole thing. Now, the reason why I like to be able to visualize this is when you get that crazy formula, the limit as n goes to infinity of, and then we have here the series from k equals 1 to n, and we get f of a plus k delta x times delta x. All right, now this formula is like, it's not 100% guaranteed to show up, and if it does, it's one question, but this is the concept of what an integral is. And it starts with a simple case of n equals 4. And the idea is that if I were to make more rectangles, because you see like this is like going over, like, oh no, it's over approximating. But what if I made more than 4 rectangles? What if I made 100 rectangles, 4,000, 40,000 rectangles? Then the error is going to start to disappear. Okay, so that's the idea with this, is I make them infinitely thin. Okay, like this. I make them like super, super, super thin. And if I look at one of those rectangles, this space here is delta x, and the height is, the function value here, f of x. So then notice if I start at k equals 1, what I'm going to get is I'm going to get f of a plus delta x plus f of a plus k equals 2. Now I get 2 delta x plus dot, 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 all the way down to f of a plus n delta x. Okay, so this is, I'm just talking concepts here. So if we look, n equals 4, see I go a plus 1 delta x. So this is like a plus delta x. This would be a plus 2 delta x. This would be a plus 3 delta x. This would be a plus 4 delta x. Okay, so like this is the concept. That gives us the height of all of our rectangles. And then we're multiplying the heights by the base to get the area, and we're adding up all of the rectangles like this. So I just want you to like actually understand, what does this formula actually mean? Okay, so, oh, Riemann sum as my insanity goes to infinity. That's funny. Just hang in there. All right. So FTC, something very practical. This is massive. Okay, this one's definitely important. So if I have a function f of t, okay, like this, then what I have is a of x is, let's say I start here at, I don't know, something like 2. So the integral from 2 to x of, I have f of t dt. So it's we call this an area function or accumulation function, because if I have a starting point here like this, then the area of this space over here depends on where x is located. So as x moves this way, the area increases. As x moves this way, the area decreases based on how I drew it. And the result of this that we really, really need to know, I'm not going to prove this because time is money, is that when I derive this, okay, what this is going to give us, let me write it like this actually. If I derive the left and right side, a prime of x is equal to the derivative from a constant to x of f of t is f of x. Okay, this one is very likely to show up in the FRQ. Something you really have to know. So make sure you know it. I'm going to show you the chain rule version. So the chain rule for, I'll just say, yeah, the chain rule variation here. That if I'm deriving integral q of x to p of x of f of t dt, this is f of p of x times b prime minus f of q of x times q prime. So for example, if I had, I'll just make one up on the spot, the derivative of integral from 0 to x squared of cosine of t squared dt. Something like this, I would plug in. This tells me to plug in to the integrand. So I'd have cosine of, instead of t squared, I would have x squared squared. But then I'd have to multiply by the derivative of the upper limit, which is 2x. And then minus cosine of 0 squared, but then times the derivative of the bottom. This piece cancels. So then I have 2x cosine of x to the 4. Okay, so that's like that formula in action. Okay, so moving on. FTC and def. All right, this one is like, honestly, like this is the poster child for Unit 6. This one will get 6 stars. Okay, even how about 7 stars? So this, if I have f of x, if you don't know this formula, you like, honestly, like people who show up to the AP test without this should just like go home and take a nap. You're going to use this formula like, I don't know, at least 8 times on the AP test, or you're going to use it a lot. So the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is the antiderivative of lowercase f. Okay, just please make sure you know this. Really big idea. And it tells you not just, I don't want to call it the area, it tells you the signed area under the curve. Because we can have a definite integral come out negative if that space happens under the x-axis. Integration by parts. All right, BC people. So AB people, I don't know, go on your phone or something for a second and take a brain break. So it comes from the product rule. So if I do UV prime, that's the same thing here as I could think of it. Well, I'm going to write out the formula first. If I have U dV, that's UV minus integral of V du. Where I remember this from is I just think product rule, that like, all right, this is U prime V plus UV prime. But then what I call it instead, I just say, all right, this, and now I just write du for U prime plus U, and then I say dV. And then I could just integrate all of these pieces. And the antiderivative of UV prime is just UV. The prime and the integral just cancel. And now this is V du plus integral U dV. And if I want to come up with a formula for this, I just subtract that to the other side. So I have, basically, you know, I'll just write it like this, minus this on both sides. And then it gives us this formula here. So it's backwards product rule, okay? So if you forget the formula, just product rule, call the U prime du and the V prime dV, and then just integrate everything, okay? Cool. Alrighty. So that is that. Improper integrals, BC. So for this one, there's 2 kinds. There's the infinite limit, like let's say I'm going from 1 to infinity. So I have something like this. And I'm trying to find this area here. So it's all about like, does it converge or diverge? So for this one, for the FRQ, what you want to do is say the limit as b goes to infinity, integral 1 to b of f of x dx. Multiple choice, please don't do that. Like if they just give you, all right, what's 1 over x squared dx from 1 to infinity, and this is like a multiple choice question, honestly, this, I'm just leaving it in terms of infinity. And I'm just going to go like, all right, antiderivative, so plus 1 divided by negative 1. And then from 1 to infinity. And that minus on the outside, I just write negative 1 times infinity to the minus 1 is 1 over infinity. Minus 1 to the negative 1 is 1. Now, 1 over infinity goes to 0, and negative 1 times negative 1 is 1. Okay, so something like this, I would not write the notation out like that. But that's improper. This is, in my opinion, the easier kind when you have, you know, an infinite limit. Okay, so infinite limit. The other kind is the discontinuous integrand. This one is tougher to deal with. So that would be if I have something like this. Let's say I call this one g of x. And let's say this is happening at x equals 2. And I want to find the area from 1 to 2. So if I'm trying to integrate up to a vertical asymptote, something like this, integral 1 to 2 of g of x, and I'm going to say x equals 2 is a vertical asymptote, then for the FRQ, I have to first identify which value is the problem. The problem is at x equals 2. And if I'm going from 1 to 2, notice I'm on the left side of the asymptote. Okay, so I just visualize this is on the left side of x equals 2. So that means when I set up my limit, I'm going to say the limit as b approaches 2 from the left side because I'm on the left side of the asymptote. And now I'm going integral 1 to b. So you see I've replaced the vertical asymptote and I have to say which side am I on the left side or the right side. And then I go ahead and I evaluate this. Okay, so then, I use the fundamental theorem of calculus and then I evaluate the limit. Okay, cool. All right. Oh yeah, the practice is going to be, I'm going to do 20 multiple choice questions at the end. I'm not going to do what's it called, like a 3-hour cram sesh. Reason being, the first 3 reviews were 3 hours, and plus I want to set a good precedent that people go to bed at a reasonable time for this test. So yeah, that's all right. Slope fields. All right, slope fields. So I think people sometimes just struggle with what is a differential equation. So I'm going to make up an easy one. And just to get the concept down. And I'll say y of 0 is equal to, how about we say -1. So if I have dy dx is 2x, something simple to start. When x is equal to 0, my slope is equal to 0. So I'm just going to make the slope field for us. Okay, so let's just say I make a slope field here. So that's at x equals 0. When x is 1, my slope is 2. So that would look, something steep. And that's all at x equals 1. When x is -1, I have a slope of -2. So I'm just doing this to get the concept down of what is a slope field and what is a differential equation, what is the solution to a differential equation. When x is equal to, so this will be at 1. When x is equal to 2, now I have 2 times 2 is 4, so it gets steeper. Okay, so this is what it's going to look like here. And when x is, so this is -1, at -2, we're going to have a slope of -4. So it's going to be even steeper. Okay, and there's going to be a point to this. So now the big technique to know is separation of variables. So dy equals 2x dx. This process is worth 5 or 6 points in the FRQ. So I integrate and I get y equals x squared plus c. But then I use my initial condition here. This is the point 0, 1. I'm sorry, 0, -1. So I have here that -1 is equal to 0 squared plus c. So my constant is equal to -1. So my solution is y equals x squared minus 1. If I locate, let me say here that -1 is over here, 0, -1. And I sketch my solution curve through here, this, if I just draw it, the slope field tells you the direction your curve is going. But this is my y equals f of x solution. So our solution is in the form of y equals f of x. The slope field comes, it's built by the derivative, but it tells you the direction the curve is going. It's mix up what does each piece actually mean here. Now, when you want to verify your answer to a differential equation, you could check it by, for one, deriving. You're like, oh, cool, this checks out with this. And then the next thing you could check is that the point 0, -1 is actually on this equation here. And it is. All right, so that's the concept behind Unit 7. Now, for the BC people, Logistic looks like this. It could be in a different form. The big stuff to know is that the curve, this is the solution curve. So this is like, y equals function of time. And we'll say this is t. Yeah, and f of t. The carrying capacity is L, and that's up here. Now, I can't remember like, oh, just memorize that value is L. The concept that I use, this is like really like, I'll just say like a helpful tip. So helpful. So a helpful thing to know about logistic. Actually, let me just, whoops, I didn't mean to erase all that. So helpful tip is this. As t goes to infinity, the function is heading to L, which is called the carrying capacity. Okay, but the sneaky one, this is the one to really know. The derivative is heading to 0. So what I like to do for questions like this is I just set this factor equal to 0. And then it tells you like, oh, the carrying capacity is when y is equal to L. So when there's actual numbers happening here, it's a nice way to just find the carrying capacity. Now, the next thing to know is that L divided by 2, this is when the growth rate is max. Okay, I'll just say the max growth rate. It is also a point of inflection. It is where the graph switches from concave up to concave down. So this is just the concept of what a logistic differential equation is and what it will tell you. All right, because if you have these ideas, it just makes the questions like easier to approach. You just want to make sure you understand what's actually happening. All right, area between two curves. So unit 8, when I have f of x and I have g of x, like this, the area of the space between them, I'm looking here from A to B. Concept is cross sections. I take one slice here. The vertical distance between these two, the same way the vertical distance between 8 and 5 is 3. I could just say, oh, that's 3, or I could do top minus bottom, and that'll tell me 3. So if I want to find the vertical distance between f and g, I just say f of x minus g of x. And the base here is dx. Now this I'll call dA. This is a thin slice of area. Infinitesimal means like Ant-Man and the Wasp level. So the area of that rectangle is f of x minus g of x dx. But this is just the area of one slice. If I want the area of the whole thing, I integrate from A to B. And there's my formula. Okay, so this is a good formula to know. Volume by cross sections, this one is like pretty rough. If I have some space here, let's say I have this, like I have like f of x and I have the x axis. And this is my region. Okay, I'll call this like region R. And let's say they go, oh, cross sections. I want you to build me a solid where the cross sections are squares. Squares is like one of the nicer cases. So I just imagine like I take those cross sections and I build them up into squares. Okay, and then whatever solid that is what I'm finding the volume of. So that's just like, ideas that you have to be able to get out there. Sometimes they'll say, all right, take those cross sections and build them into semicircles. And then you do this. Or they'll say, take the cross sections and turn them into equilateral triangles. And then find the volume of that shape. Okay, so if I had to, like, let's say, turn this into a semicircle, let's say I take one of these slices here and I turn it into a semicircle, the diameter of this is f of x because it's going from the x-axis up to the curve. So the radius would be f of x over 2. And, let's say I'm going from A to B. So then the volume of one slice of this, like if I'm using the semicircle, is pi times the radius squared dx, because this dimension here is dx. But then I have to divide by 2 because it's a semicircle. So then if I plugged it all in, it'd be dv is pi over 2, f of x divided by 2 squared, and then dx. And then, full area, I would integrate from A to B. Okay, so you really want to be able to draw these out and just get what's going on here. And it's the same idea when we're doing volume of revolution. Now, let's say I make up a tricky one here. I have, let's say I call this F, and I call this G of X. And let's say we're going here, where this is the line. I'll call that like Y equals C1. So I'm going to take this region and rotate it about that. Well, I draw my cross section. In this case, it would be a washer. I'm sorry. Yeah, no, it would be a washer. It would have a gap. See the gap here. So I draw one of them out. So here's my cross section here. Is the washer. And the inside is cut out. So that means here I need an outside radius and I need an inside radius. The volume of a washer is pi times outer radius squared minus inner radius squared. Okay, it's like I'm doing like the circle on the outside minus the circle on the inside. And then just times dx because it has volume. But here, the concept, just think top minus bottom. And if I look here, this is the center. Okay, like this is the piece going through like this. So my outer radius would be the top is C1 minus outer radius goes the entire distance. It would be C1 minus G of X. And then my inner radius would be the shorter distance to the center, would be C1 minus F of X. Okay, just make sure that you are using the center. I'm going to say don't for this. For revolution, don't say F minus G. Okay, some people just say, oh, F minus G squared, but that's not what's happening here. We're not finding the area between the curves. We're finding the volume by revolution here. So then this, if I had to turn it into an integral, let's say it's going from A to B, this would be integral A to B of pi times, and then I have outer radius squared minus, and then I have inner radius squared. Okay, so the inner radius squared, C1 minus F of X squared, and then dx. Okay, put a bracket at the end like this. Cool. Arc length. So BC. For arc length, I'm going from A to B. All right, if you just want to memorize the formula, it's integral A to B square root of 1 plus F prime of X squared. All right, this one is like pretty nice to use. I don't think it's like the worst formula in BC. This is like one of the easier topics, I think, out of BC. The concept, though, is cross sections. I take a tiny piece and I calculate the rise is dy, the run is dx. And the small change here is the length of the curve. That's dl. That's a tiny slice of the length of the curve. If I do dl squared, that's equal to dx squared plus dy squared. Okay, then I go like this. And now check out this algebra. dl equals, I'm going to factor out a dx squared. And that's going to leave me with 1 plus dy squared over dx squared. Take a second to look at that, and you see if I distribute, it brings me right back. So now I'm going to erase this just to show you that the formula works. Okay, it's a Pythagorean theorem concept, but it's Pythagorean theorem, you know, at Ant-Man and the Wasp level. Oh, the board is freaking out. All right, let's get it back here. Okay, so now I have dl equals the square root of dx squared. This pops out as dx. But now I have 1 plus, and I'm going to write dy dx in parentheses and then squared. Okay, so notice that's giving us basically the formula. The last thing to do would just be to integrate from A to B. Then I could say the length of the curve is the integral from A to B of 1 plus dy dx squared dx. Okay, which is also the same thing as f prime. So that is our arc length, right? It's the concept, once again, to really know is infinitesimals. All right, limits honestly build the entire class. All right, motion problems, position. Let's say I call it x of t. Velocity is the rate of change of position. Acceleration is the rate of change of velocity. Position tells you if like we're on a horizontal line. This is the Calc AB version. We only move in one dimension. Position tells us where we are. Velocity tells us how fast we're going and what direction. Acceleration tells us where we want to be going. Okay, so if I'm going left, my velocity is negative, but I'm accelerating to the right, then I slow down, and then I eventually go to the right. Okay, so displacement, this is my change in position. I integrate the rate of change of position, which is velocity. Normally, we call velocity, v of t, and I call acceleration a of t. So displacement would just be the integral of velocity from a to b. Okay, total distance is the integral of speed. And I'll say here, speed, if you don't know, is absolute value of velocity. The speed is just the magnitude of your velocity. Direction doesn't matter. So total distance is the integral of speed. Okay, and some other things to know. When v is greater than 0, you're going, the particle goes to the right or up. When v is less than 0, the particle goes down or to the left. And when the velocity changes signs, the particle changes direction. Parametric, first derivative, dy dx. So parametric is when we have a function where the x and y are mapped with a parameter of time. Okay, so I could be here at like t equals 1, then I could be here, and then I could move backwards. Okay, so there's a time component. But the first derivative is dy dt over dx dt. The second derivative, d squared y over dx squared. The formula is the derivative with respect to time of dy dx over dx dt. Now, for motion problems, just know that you have your position function. Let's say my position function is vector valued x of t, y of t. Then my velocity function would be x prime, y prime. Okay, so this is just building off of before. My acceleration function, probably be able to say this part, is x double, y double. All right, speed in parametric is the square root of x prime squared plus y prime squared. So make sure you have these formulas down. And the distance that you travel is equal to the integral from a to b of speed. All right, these have the potential to be like the easiest points on the test if you have a calculator, unless they like really spice it up and make it crazy. Oh, and I'll say your position at b is equal to your position at a plus integral a to b of x prime of t. So this is really just the fundamental theorem of calculus. And it's the same thing for y of b. Is y of a plus integral a to b y prime of t. All right, so formulas. All righty. Parametric is not an AB, so don't worry. If you're, like, oh no, was I supposed to? You were not supposed to learn that. Not to worry. All right, and now polar, everyone's favorite. Polar, we have to know that when we're deriving polar equations, we have a few things. Polar coordinates, just know that you have r and theta. Okay, they're in the form of r comma theta. So if I get the point, like let's say 2 comma pi over 4, this tells me to go out 2 and rotate the theta equals pi over 4 like this. So I'm going out 2, and then like I rotate this way, and that would send me here. Okay, so it's circular motion now. That's how we get around. If I had the point, let's say negative 2 pi over 4, what if r is negative? Then I'm facing this direction, but instead of going out 2 and then pi over 4, I'm going to go, I could get there two ways. I could go to the left 2, I could start on the negative x, and then rotate pi over 4 here like this. So that would put me here. Or I could face pi over 4, and instead of going 2 units northeast, I go opposite northeast, which is southwest. So I just go opposite. All right, the derivative of a polar equation. So ones you really want to know is this. X is r cosine theta, and y is r sine theta. This is just from basic trig. What I mean by that, I'll just write it over here. When I have, and I'll just make a curve here. So this is for polar. When I have a polar curve, any point, I'll call it xy. If I want to find the polar coordinates, if I'm going over x and I'm going up y, in polar, I go out r and I spin theta. So if you look here, if I did cosine of theta, see how that's adjacent over hypotenuse? It's x over r. And then I cross multiply and it gives us this one. Okay, and then same thing for sine theta gives us this. Now, the reason why I bring that up is the derivative dy dx is similar to parametric, dy d theta over dx d theta. See how it's like the same concept. I forget this formula every day. I'm not lying. I don't know this formula. What is dy dx? The slope of the tangent line to a polar curve. I don't know. But I do know the product rule and the chain rule. Dy d theta, I'm going to derive this with respect to theta. The derivative of r is dr d theta times sine theta, and then plus r times the derivative of sine is cosine. And then over the derivative dx d theta, now I'm deriving this one. With respect to theta, I'm going to get dr d theta times cosine. And then I'm going to get plus r times the derivative of cosine is minus sine. So here is the formula here. Okay. Now, area of a polar region, let's say I want to find the area from, let me just erase this. So I want to find, now I got to redraw things a little bit. This area here, from here to here of the polar space. I'm going to take out a cross section like this, and I'm going to zoom in. So there it is. It's like a slice of pizza. I'm going to call that r, and d theta is a small change in the angle. The area of this is a sector, is pi r squared, but I'm only taking d theta. I'm not taking the whole circle. I'm taking d theta out of 360 degrees, but I'll say 2 pi radians. And now this gives us the area of a slice is 1/2 r squared d theta. Now, if I want the full thing from theta 1 to theta 2, then I just integrate from theta 1 to theta 2. Okay, and that's why the area of a polar curve is here. Okay, the cross sections are sectors, which are in the infinitesimal world, though, little slices of pizza, thin slices. When there's two curves, like let's say I have like a function going outside like this, then I just do 1/2 theta 1, theta 2, outer radius squared minus inner radius squared, d theta. Okay? So just saying the formulas out. That's the concept. Okay, I do the outer one minus the inner one. If I want to find, like, let's say, I'll clean that up though, because this looks sloppy. Oh, wait, yeah, it's like an autopilot now. I drew it once and now it's just going to erase itself. All right, so if I had, let's say, something like this, and then something like this, and I want to find the area of this space. So this would act as like my r outside, and this would act as my r inside. Okay, and then theta 1 would be this angle. Theta 2 would be here. All right. Finally, unit 10. What does it mean for a series to converge? So for a series to converge, when I have something like this, let's say n equals 1 to infinity, and this is like a1 plus a2 plus ... plus, like a sub k plus ... is that this entire sum is heading towards an actual value. Okay, if it does not converge, then it diverges. Sometimes you could have this here going to infinity, or sometimes it oscillates. Okay, so these are just examples of like what could happen. You know, like if I had like an easy one that diverges, I'll just make up a really obvious one. If I had like, all right, this series from n equals 1 to infinity of just n, this would be 1 plus 2 plus 3 plus 4 plus dot, dot, dot. We could see that this is just growing out of control very quickly. So that's going off to infinity. If I have something, you know, and the nth term test told me that this is going to happen, that when I take the limit as n goes to infinity of just the summand, the term inside the series, and it's non-zero, then my series automatically diverges. The only shot we have at convergence is if the series, the terms shrink to zero. And it's a question of big ideas. Do the terms shrink fast enough? Okay, like if I have sigma 1 over n, this diverges. Okay, but if I have sigma 1 over n squared, this one will converge. Okay, because 1 over n squared shrinks faster than 1 over n. All right, and that's trekking into this territory here, the p-series test. The comparison test, I would say limit comparison test is a little bit more important. Okay, this one I would say is like 2 stars. Direct comparison, I'll give it like 1 star. All right. The integral test, I only use it if they tell me to. Okay, so this one is like a, yeah, this one, double star. Okay, ratio test is big. All right. Also, I should have wrote it here also, the geometric series. Okay, for a geometric series, that test is, you know, also a good one. They like that as a multiple choice question. This one's also big, not as big as the ratio test, but it's like fairly popular. Okay, the alternating series test. All right, and then knowing how to determine all this. Now, a power series. What is a power series? So if I give you this one, this is just like a plane series. Okay, like let's say from n equals 1 to infinity. But then the moment I do this, let's say instead of 1/2 to the n, I say, all right, f of x equals n equals 1 to infinity, x to the n. Now I have a power series because this has a variable x to it, and I could express it as a function. So I could say something like, oh, f of 1/3 is now sigma n equals 1 to infinity of 1/3 to the n. And when you have a power series, you could start finding things like the radius and interval of convergence. A Taylor series is an infinite, is a way to express a function of x as an infinite polynomial. Okay, so Taylor series, this formula is really, 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 really big. Okay, this one is like a big part of Unit 10. So you really want to make sure you have this one down. Okay, make sure you have this. All right, this is the packaged version. The expanded version is this. Like I have, let's say, f of c plus f prime c x minus c plus f double prime of c x minus c squared over 2 factorial plus dot, dot, dot. All right, now the Taylor polynomial is, let's say I chop this and I stop it at 2. And I have like just f of x equals f of c plus f prime c x minus c plus f double prime c x minus c squared over 2 factorial. Now it's finite. Okay, so this is the thing to know. And then the two error bound formulas are alternating series error bounds and the Lagrange error bound. Okay, so also Lagrange, right? Error bound. The alternating series error bound might be, I think it's the easier one. It's debatable, but I think it is. And let's say I have this series here. So n equals 1 to infinity of like -1 to the n over n. And you know what? Let me make it start n plus 1. so that it's 1 over 1 and then minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5 minus dot, dot, dot. So the alternating series error bound, I'll use that first. Let's say the whole thing here, like this converges and it converges to S. S sub 1 is just 1. S sub 2 is 1 minus a half. S sub 3 is 1 minus a half plus a third. And I'll do one more. S sub 4 is 1 minus a half plus a third minus a fourth. So let's say here, I don't know what S is, but I go, all right, S, I'm going to say that S is roughly equal to S sub 4. Like I'm just going to do these terms. Well, notice that if I stop here, I just use 4 terms. Okay, so S minus S sub 4, then this represents my error. With my S sub 4 approximation, my error bound is going to be less than or equal to the first term that I didn't use, the absolute value of it, which is my 5th term. So yeah, like this is my first term, second, third, fourth. The first unused term is your error bound. Okay, so this here would count as my error bound in this case. So I would say that how far away is the actual sum from whatever S sub 4 is? And let's say we actually work that out. So that's 4 over 4 minus 2 over 4. Actually, no, I need a better comment. I'm going to have to use 12. Right? Yeah, that's the, so 12 over 12 minus 6 over 12 plus 4 over 12 minus 3 over 12. So this makes 6 over 12 plus this makes 1 over 12. So the actual S sub 4 was 7/12. Okay, so that means that S minus 7/12 is less than or equal to the first unused term is 1/5. So that means that we're within 1/5 of the actual value. Now, if I want to do a little algebra here, I could say that the actual sum minus 7 over 12 is between negative 1/5 and 1/5. And then if I add here 7/12, this will give me an interval for where our actual sum is. Okay. So yeah, something like this. I mean, I'll just leave that part. I'll just say that it's a 1/5 plus 7/12. And on the other side, it's 7/12 minus a fifth. Okay. But the formula is that the actual sum minus the nth partial sum is less than or equal to the first unused term. Okay, so like this is. And now, however, I'm only allowed to use this when I have an alternating series and the terms are decreasing in magnitude to 0. For the FRQ, they love this phrase. That we have an alternating series, the terms of the alternating series are decreasing in magnitude to 0. Okay, that's big. All right. Cool. So moving on. Now this one is for Lagrange, and this is like from an actual like old test. Okay, I forgot what year it is, but I like this question because this was like a tougher Lagrange, and this was like part D of whatever that question was. So the Lagrange error bound formula, if I have something in this form here, will tell me that when I have f of x, okay, and I could write it like this. I could say like the absolute value of f of x minus like p, sub n of x, when I use an nth degree Taylor, is less than or equal to the n plus 1 derivative at z times x minus c to the n plus 1 over n plus 1 factorial. So this is my Lagrange error bound formula that, I'm going to use here. And let me just put this in 2-page mode. So for this formula, it's a little messy. Like n is like the degree. So n is the degree of the Taylor polynomial. X is the value plugged in. So is the value plugged in to the function. The value C is the center. Okay, and then probably the toughest piece to learn in the beginning is Z. So Z is the value of X between X and C that makes the m+1 derivative. Or I'll say the that maximizes the m+1 derivative. So that makes the m+1 derivative as big as possible. All right, but this part here, I'm going to kind of like underline, because for the interest of AP calculus, they're not going like super, super precise. And you'll see what I mean in a moment. So here I look at this expression and I say, all right, so we have absolute value of P sub 4 of 1/4 minus f of 1/4. We want to show that this is less than 1/3000. So what I'm looking at here is I'm saying, all right, n is 4, the x is 1/4. The center of the series, this is about x equals 0. So our center is at 0. And the z value, like this, is going to be the tough part. Okay, but if I just set this thing up, I'm going to say that this whole thing here, so this, which I'll shrink down, is going to be less than or equal to, if n is equal to 4, the m+1 derivative is the fifth derivative at z, times x minus c, so 1/4 minus 0, to the power m+1. If n is 4, m+1 is 5, and then over 5 factorial. Okay, so here it is. But now this is the part, like I said, that when people mess up, they're most likely to mess up this. So z is the value of x between x and c. So I'm thinking here the z value is between the center 0 and 1/4. So it's somewhere here. Okay, and it's going to make, so you see how 0 to 1/4 is here. That's 1/4. And it's going to make the derivative as maximum as possible. Now, this is why this was like kind of a mean question, is people were like, oh, 35. And I think they showed mercy if you picked 35, but the rubric, they went over and just said, you know what? Let's just go with 40 to be safe. That an error bound is never going to be like 100% precise, meaning it's not going to tell you the exact error. It's just going to bound it. So here, they let this value equal 40. They just kind of rounded, because like I wouldn't put all my net worth on this being, let's say, equal to 30 or 35. Like, I might need reading glasses soon. So that's why they just pick something that's clearly above. And then watch what happens. If I use 40, now I have 40 times 1/4 to the 5th power. Okay, so we have 1/4 to the 5th power. And now we are dividing by 5 factorial is 120. This simplifies to 3. And if I do 4 to the 5th power, all right, I could just sit on the side here and do long multiplication. At the AP test, I would just trust that it's good. But 4 to the 5th power is 1024. So if I do 1024, then times 3, this is 3072. Okay, so this whole thing is 1/3072, which is definitely less than 1/3000 because the denominator is greater. Okay, so that's as bad as Lagrange gets. The nicer way, when they want to be nice, like the nice version, or you could say like the polite version, is when they go, oh, by the way, the absolute value of the 5th derivative of x is like less than or equal to 40. Then you just plug in 40 and you don't have to think. Okay, so when they make a graph, a lot of people messed this up and they were like, oh, let me choose like 120. They just went way too high because they saw the highest point, or maybe they went even a little bit above that. Or they, maybe by here they pick like 90 or 100 or something. So just make sure you're only looking, the Z value is between the X that's being plugged in, 1/4, and the center 0. Okay, so tough question. Alrighty, cool. So that's the crash course of the topics. I guess here I should switch over to the, what's it called? I should switch over to the multiple choice. All right. I did say like I was gonna like try to cut this a little bit shorter. 9:24 though. I'll say East Coast people consider like just getting a good night's sleep. West Coast people though, like for sure, and maybe like Central, like Texas and whatnot, or international, depending on what time zone you're in. You might be able to just stick it out longer. Okay, so now I am going to move to this phase. Okay, I'll just do 20 quick multiple choice. I just thought there, like, for me to just go through a lot of FRQs. I did that the night before, and what's it called? Yeah, I just didn't think it would be like a ton of value, like just doing the same thing that you could just watch the replay for. Okay, so here I'll press save. Why not? Oh, maybe later. Did it crash? All right, whatever. As long as it closed. All right. So ignore. All righty. So let's see. Question 1. I'm just monitoring the chat here. Oh, all right. And just yeah. Okay. All right, moving on. So let's see. We have question 1. Okay. Question 1. Yeah, I was just monitoring the chat because if people are spamming and just saying silly things, then they will be booted. All right. Yeah. So looking here, graph of the function f is shown. Which of the following statements about f is true? So one thing that jumps out at me right away is that we have a removable discontinuity at A, and we have a jump discontinuity at B. So that's jumping out. So here, which of the following statements about f is true? I'm looking at this, and this answer choice jumps out right away. The limit as x approaches A. So as we approach from the left and right side, we are heading to a y value of 2. But why are the others no good? The limit as x approaches b of f of x equals 2. This one's no good because the limit at b does not exist. And the reason being that the left side limit is heading to 2. The right side limit is heading to 1. So this would be true, like a correct choice C would be the limit as x approaches b on the left side of f of x is equal to 2. Like then it's correct, but that's not what it says. The limit as x approaches b in general just does not exist. The limit as x approaches a does not exist is not true because the limit does exist. F of a is undefined. Like that's a fair statement because there's a hole in the graph, but that doesn't mean the limit doesn't exist. And then the limit as x approaches a of f is equal to no, this is not true. Okay, that part there is no good. So 1 is B. All right. So here, for what values of x for which the function f is defined by this, like basically for what values of x is f increasing? So here, if you want to use the product rule, you could say u is equal to x squared minus 3. You could say v is equal to e to the negative x. And then u prime would be 2x. v prime would be negative e to the negative x. So then I would have here, if I find f prime of x, I could say is 2x e to the negative x. And then I have minus, because I'm doing a positive times a negative, and then times x squared minus 3. So then from here, I could factor out e to the negative x. And we're left with 2x minus x squared minus 3. Now the minus goes through, and this becomes e to the minus x. And I have 2x minus x squared plus 3. Now this one, personally, I mean, I guess, yeah, you know what? This one I would want to write the negative on the outside. So I would take a negative out, and then I'll have a positive x squared minus 2x and a minus 3. So then this I could factor. That's x minus 3 times x plus 1. So there's f prime. Okay, now from here, I note that this is always negative. The reason being, e to the negative x looks like this. It's always positive, but if I put a minus in front, now it's always negative. This is going to give me roots of x equals 3, x equals negative 1. So that's when f prime is equal to 0. So f prime, now I make my sign chart at negative 1 and 3. And for this one, I'm imagining a parabola like this. If the roots are at like negative 1 and 3, then it's going plus, minus, plus. However, the outside is always negative. So if I'm doing this is positive, the quadratic piece is positive before negative 1, but the minus e to the minus x is always negative, then this is going to go minus, plus, minus. Okay? And for this one, we want to know where is f increasing. It's looking like D. So this one here, though, to be 100% sure, just in case, because I'm going fast here, because, yeah, I'm definitely like feeling a little bit fried. Let me just see, did I? Oh, no. So that was, okay, so I'm at a full screen. Yeah, like this is like borderline, like a little bit cruel to do this without a calculator. I mean, it's fair game, but, and yeah, like I said, I'm like kind of going a little fast here because, all right, let me see. So we're going, the critical points, we're at negative 1 and 3. So when we graph this, I mean, I guess this is fine. So from negative 1 to, oh, so here's our function. And let's just see here. From negative 1 to 3, the function is going up. Okay, we can see 1, 2, 3. So that looks good here. Now, if I really want to be sure, I would graph the derivative, math 8. And I'm deriving with respect to x, alpha trace y1, x equals x. And if I look at just the red, and this one, let's say I shrink to like negative 3 to 3. Yeah, see, from negative 1 to 3, our derivative is positive. So that answer is looking good. All right, here's a nicer one. We don't have to really worry about all that extra stuff. So here we have a graph of f prime, the derivative of f, and we want to know which of the following describes all of the relative extrema of f on the open interval AB. Well, we have 3 critical points. And notice if this is a graph of f prime, the sign change is going from negative to positive. And remember what I said before, if our slope is going negative positive, this makes a local minimum. So this is the site of a local minimum for f of x. And then here we have a sign change from positive to negative. So in terms of, oh, and they use relative, which is like the same thing as local, has the same meaning. So relative minimum, relative max, like if I keep track here. So relative minimum, I have 1. Relative maximum, I have 1. And then here, I have another sign change from minus to plus. So I have 2 relative minimums. Okay, so that's 2, not, and maxima is maximum. So let's just see. We have 1 relative max. So that's maximum first. So 1 relative maximum and 2 relative minimums. Okay, so there's 3 critical points in total here. So I have 1 relative max and I have 2 relative minimums. All right. Question 4. So here, y is a function of x such that y prime is greater than 0 and y double is less than 0. So this makes me just think like, oh, y is increasing. Okay, so I don't know what happened here. So I'll just say y is increasing. All right, so that's the idea. Y is increasing. And that's from this. And now this, y double negative, so y double less than 0 means it's frowning. So if we're increasing and frowning, then the graph is going to look like this. Okay. Yesterday, I believe I wrote it like this. I showed you the 4 emojis. When we have plus minus, the curve is increasing and frowning. So it would have to be choice B. That's the one that looks like this, if that's happening for all x. If I had plus plus, it's going up with a smile. If I had minus plus, it's dropping with a smile. And if I had minus minus, it's decreasing with a frown. I call those like the 4 emojis of curve sketching. Question 5, something conceptual. So here we have h of x is f of 2x. So right away, I'm going to find h prime of x is f prime of 2x, but then times the derivative of the inside is 2. So when they say h is increasing on 2, 4, the problem with this right away is that this is just a table with select values. So we don't know everything that's going on between 2 and 4. These are only like, so right away, like 1 is not looking good because we only have select values. Like there could be a whole lot happening at, let's say, x equals 1, x equals 3, x equals 3.5 that we just don't know about. So anytime they're making a statement like this, that h prime is basically always positive on this space, like that's not looking good. They're basically saying that f prime is always positive, and you might look and say like, oh, it does look like it's always positive, but there could be stuff happening between. So that's why be careful with those. But now this is looking like I have h of x and I'm talking about h of x. This looks like IVT. So IVT, if I find h of 0, that's f of 2 times 0 is f of 0, and f of 0 is equal to 3. Now I find h of 4. H of 4 is equal to, I got to be careful for this one, f of 2 times 4, which is f of 8. And f of 8 is equal to 13. And now here's the idea. Since we have differentiable function f, and h is basically like the composition of f of 2x, which is like another differentiable function. So h is differentiable. H is differentiable means that h is also continuous, which means IVT and MVT both apply. So here, if you just think about it, h, whatever it looks like, is at 0, it's at 3. So this is at 0, 3. And then when we get to h of 4, we're all the way up here at 13. We want to know, is it possible for the function to hit 12? It absolutely has to, because if the function is continuous, it has to at some point pass through every value between. Okay, the sentence, like if this was the FRQ, I already said that h is continuous. I would say, since the value 12 is between f of 0 and f of 8 by IVT, there exists a value c between 0 and 4 such that, oh, and let me just call it h of 0 and h of 4. That would be a better way to say it. So let me just fix that up. So we have h of 0 and h of 4, such that h of C is equal to 12. Okay, so that one is good. That would be if it was FRQ. So this one is true. So it can't be 1 and 3 only. And 2 is a contender for the others. 1 we eliminated, so it can't be all 3. So it's just a matter of, is Roman numeral 3 true? This one is using MVT because they're referencing the derivative. Is the instantaneous rate of change going to be equal to the average? So really what we have to do here is just find the average rate of change on 0, 2. So what is the average rate of change of H on 0, 2? So this one I'm doing H of 2 minus H of 0 over 2 minus 0. And this is going to be F of, remember I plug in 2, I'm going to have F of 2 times 2 is 4 minus F of 0 over 2 minus 0. And I'll write the result. Over here, F of 4 is equal to 9 minus F of 0 is 3 divided by 2 minus 0. Sorry, the 0 got, either I wrote a 1 or the pen freaked out. And now this is equal to 6 divided by 2, which is equal to 3. So MVT would guarantee that at some point that there's going to exist a C value such that H prime equals the average rate of change, and the average rate of change is equal to 3. So this one is also true. It's got to be choice C. Okay. All right. So let me just see here. All right. Just seeing where we are at. All right, we have a nice crowd of people here, and the group is growing. Yeah, you get a break after the first part. All right. So this one is this is a popular question. You could I would say you could expect something like this tomorrow. So they have G is an antiderivative of F. So if I have F of X like this, and I want to know here what G of 1 is. Okay. So I want to know what G of 1 is, and I know what G of 3 is. Now you might be thinking, wait, why would you write it backwards? Because this is a calculator question. So it doesn't matter. You'll see why I'm doing this. So this is what I want to know. What I want to know is going here. And what I was given is going here. So if G is an antiderivative of F, I use the fundamental theorem of calculus. The antiderivative of F is G. And then I do G at the upper limit 1 minus the lower limit is 3. So if I want to know what is G of 1 equal to, I just do plus G of 3 on both sides. Okay, so then G of 1 is equal to G of 3 plus the integral from 3 to 1 of F of X. So this is just calculator work. G of 3 is 5 plus integral 3 to 1 of square root x to the third plus 2 dx. Okay, so this I'm just typing in. I'm doing 20 because I spent that first part going over big ideas. I don't have it in me to do like a full 3 hours today. I would say, the replays of the first 3 days, unless you watched all 3, then awesome. I didn't see who wrote that comment. I just kind of skimmed. But yeah, I'm going to get caught up. Let's see. Yeah, it's like almost 10 o'clock. So I would prefer not to stay on till midnight. I stayed on like pretty late the other nights. I wound up going like 3 hours and like 20-ish on day 3. So people on the East Coast, I would say it's probably a better idea you get some rest. Okay, so 5 plus, so it's negative 1.585. So negative 1.585, which looks like this one here. Okay, so that is the value that we're starting with. All right. So one thing, to point out here is it's all about I guess the direction that we would be going. That 3 is the starting point. So if we go backwards, our area is going to go negative. All right, so yeah, that's how we do this question. One thing to be careful of for these questions, though, is if you just write this without the 5 plus, like you leave out the initial condition, you could guarantee that answer is going to be waiting. And you see, -6 point. Well, people might just flip it and make it positive, but they're going to tempt you to do like a lot of combinations of wrong stuff. So just be on the lookout. All right, here's a nice question. No calculator needed. So this one, they're telling us capital F prime equals F. That means capital F is an antiderivative of lowercase f. So here, when they give us this, and they want us to find f of 3 minus f of 0. So what we could do here is we could just set up this integral, okay? And think about what is it actually telling us. So that's what we're going to do here. Like, how do we build this piece up? Okay, so I'm going to go 0 to 3 of f of x and just see where this takes us. I do the antiderivative of lowercase f, and they're saying here in fancy language that capital F is the antiderivative. But now I have to break this into pieces. So what I know here is that this part is a horizontal segment. Okay, so that means like the area from 0 to 1 is just the area of this rectangle, which is going over 1 up 2. So the area here is 2. So the integral from 0 to 3 is the same thing as the integral from 0 to 1 of f, plus the integral from 1 to 3 of f of x dx. And this would be equal to the antiderivative at 3 minus the antiderivative at 0. So now this piece, I'll just write the result over here. So let me just say this, that f of 3 minus f of 0 is equal to the integral from 0 to 1, the area is 2. We could just use geometry. Plus the integral from 1 to 3 is 2.3. So this will work out to 4.3. Okay, so this is going to work out to 4.3. Cool. Moving on. Use substitution. There's a few ways you could do this. You could rewrite this first as e to the negative x cubed times x squared dx. And then just say u equals negative x cubed. Du is negative 3x squared dx. And then from here, there's a few ways we could do this, but I personally like to solve for the leftovers. You see how there's an x squared dx? I want to get that by itself. So I could divide both sides by, let me change colors. I'm going to divide both sides by negative 3. Okay, so over negative 3. And now this tells me here that negative 1/3 du, that's du over negative 3, is negative 1/3 du equals x squared dx. So now I'm just going to write this integral over here as, let's see, we're going to have e to the u, that's negative x third is u, and then x squared dx is negative 1/3 du. And now the negative 1/3 just tags along for the ride, and the antiderivative of e to the u is e to the u plus c. So this is negative 1/3 e to the negative x third, and then plus c. Okay, so where is that? And it looks like this one. Like they take the e to the negative x third and they send it back down. Now, if you want to, what you could do is you could check your answer. You could derive your answer and see that it actually matches up. So that's something like if I have the time, I am going to spend the time to do that before I move on. So if I derive, let's say, negative 1/3 e to the negative x third. This is negative 1/3. Then I have e to the negative x cubed. Whoops, let me, oh, this got, yeah, moved over. Hang on, let me fix that. Okay, so e to the negative x cubed, but then chain rule, I'm doing times 3x squared. I'm sorry, I'm doing times negative 3x squared because my exponent is negative x third. And then negative negative goes positive, and 3 times a third is 1. So this makes x squared e to the negative x third. The plus c, the derivative is 0. So I could say like, yeah, plus c, and I get plus 0. And that just brings me back to the integrand. So that's how I know I'm happy with that answer. All right, so 2 questions that are connected. Motion. What is, we have a bug that is crawling up a vertical wire. The velocity of the bug is given by the graph. So this is a graph of velocity. At what time t does the bug change direction? That's when v changes signs. Okay, so when velocity changes signs is when the bug changes direction. So the bug, if it's going on a vertical wire, so like what's actually happening here is it's like the bug is going up because the velocity is positive. So the bug is going up. It's like increasing its speed. Then it's maintaining its speed. It's going at constant velocity, 3. Then it decreases its speed. And then eventually the velocity is 0 and it goes backwards. Okay. The velocity changes signs at 6. It goes from positive to negative. Okay. So the bug is going from up to down at t equals 6. What is the total distance traveled by the bug? Total distance tells us like if the bug is going up and then down, when it goes down, we're just going to treat that as it's going in the same direction. So here, what you could do is you could find the area of this trapezoid, okay? Because total distance is the integral of speed, and we're going from 0 to 8. So here, if you want, you could reflect this over. You could take the absolute value of velocity, and that just reflects that triangle up. All right, so then it just treats it all as positive. And now I have the area of a trapezoid is 1/2 height, base 1 plus base 2. The bases are the parallel sides. So here I would have 1/2. The height is the distance between the parallel sides is 1, 2, 3. And now the bases, once again, are the parallel sides. That's 1, 2. Plus 0 to 6 is a jump of 6. Okay, and then I have plus, the second shape is a triangle. 1/2, the base is 2, the height is 1. Half of 2 is 1. So now I have half of 8 is 4, times 3 is 12, and 12 plus 1 is 13. So choice B. Alrighty, so moving on to question 11. Something like this, though, we would need a calculator. So what is the area of the region in the first quadrant enclosed by the graphs of cosine x and y equals x and the y-axis? So here, I'm just imagining cosine is going down like this and then back up. So if I'm in the first quadrant, I have this, I have y equals x, and I have the y-axis. My region is here. Okay, that's what I'm finding. So one thing I need to know here is like, what is the x value here? I know that this is x equals 0 because that's the y-axis. But what's the mystery value here? And now the concept from before that I was saying is top minus bottom. That if I want to find the area of one of these cross sections, the rectangle, the base is dx, the height is the distance between these two, and the top is clearly cosine, and the bottom is x. So I just have to know, when do they intersect? And that's what the calculator is going to tell us. So I'm going to have, eventually though, that the area of one slice is cosine x, and then minus, fix that up, cosine x minus x dx. And I'm just integrating this from 0 to mystery value. And that's all I have to really find here is the mystery value and then plug into the calculator. So we have cosine x and we have x. And I'm in quadrant 1. So 0, I could just even go out to probably like 5 is fine. And then let's say 0 to 3 is fine too. So here's that intersection point. Second trace 5. And where am I? Wait, where did I? Oh, I have to go towards like x equals 1. So I'm following the x. See, I have to go before 1. There it is. Okay. So I just get close and I press enter 3 times. And there's the intersection point. So second quit, and then I hit second answer. To get this, I could store this as the letter A. And now, math 9, we're going from 0 to that value A, not x, A, and it was cosine x. Close the parentheses here, otherwise you're just going to get cosine 0 is 1, minus x dx. We get 0.400. So this is, oh yeah, so whatever that, I'll just say that value was equal to A. So the area equaled 0.400. All right. So that is 12 coming up. Now that was 11 that we just did. So here we have the region enclosed by the y-axis. Let's see, y-axis. Then we have, so this is one of the boundaries, y-axis. We also have the line y equals 2 and square root x. Okay, so the boundary is here. See that? That's our boundary. Square root x just exists in quadrant 1. So that's, yeah, where our region is. So now we're taking this region and we're revolving it around the y-axis. All right, so this, we just have to be careful. We're using a horizontal slice and going this way. The cross section is going to be a disk because we're going around the y-axis and the region is against the y-axis. There's no gap. So here I have a horizontal slice. So I need to square both sides. I'm going to say y squared is equal to x. So I need everything in terms of y. I'm going to have y limits. I'm going to have dy, and I'm going to have a function of y. So this horizontal distance is x, but x is equal to y squared. So the radius of this is going to be y squared as it spins this way. So then the volume of one of these is pi times the radius squared, but then dy. The radius is y squared. So I gotta, don't say, oh, how cool, they put a square. I don't have to write it twice. You absolutely have to write it twice. And now my limits are going from the low point to the high point. So from 0 is the low, 2 is the high. So the volume, and I'll just say that this is pi times integral 0 to 2 of y to the 4th. So now I can say the volume is pi times 1/5 y to the 5th from 0 to 2. And now this is pi over 5. I'll just combine those two times 2 to the 5th minus 0 to the 5th. This is gone. And this will simplify to 2 to the 5th power is 32. And then pi over 5 makes this choice A. So nice question. Oops, sorry, that was loud. Just, yeah, I've been writing a lot. Okay, cool. How are we doing in the chat? Let me take a pulse here. Everyone doing all right? Oh, thank you for the tip. I appreciate that so much. Thank you. That was very kind. Oh, all right. Shell method, yes. If you know the shell method, then use it. The shell method is not on Unit 8's curriculum map anymore. So, yeah, that's just not there. If you know it though, awesome. I'm not going to teach the shell method right now because it's not on the test, but awesome that you know it. All right, so let's see. Using the 5th dimension. I hope not. 5th dimension sounds scary. Can barely handle 3 dimensions. All right. Oh, just do your best. Look, about like just to give you all like I guess maybe like a little inspiration or just reality. Tomorrow is just another test. some people in the world are going to get 5s, 4s, 3s, 2s, and 1s. And whatever happens, it's one day. It's just telling you where you're at right now. It's not going to tell you where you're going to be. So, kind of like if we use position, velocity, and acceleration. Okay, so tomorrow is just going to tell you your position. Okay, your real desire, though, like if you want to change your situation, you want to think about accelerating. Okay, you want to accelerate, that's where you want to be. And if as long as you like have a goal, like, hey, I want to be there, and you like stay committed to that goal, like eventually your velocity is going to be going like in that direction also. All right. So some people may like, well, I made some bad choices this year. Like I didn't study a lot, or I didn't do my homework, or I was on my phone too much, whatever it may be. All right. Not a judgment. Like, a lot of people do that. I wasn't getting straight A's all the time. But when you find your goal, it's like, all right, now I know where I'm accelerating towards. And yeah, you may be going the complete opposite way, but your like engines are like now thinking like, yeah, we're firing that way. And eventually I'm going to be going that way. So tomorrow, like, yeah, it may not be realistic for everybody in the world. Like if it's 11 o'clock at night and they're just like, hey, I want to get a 5 now. And they were asleep like the whole school year. It's probably not going to happen, but there's optimism. Like it's a lot of time could really change a lot if you have a clear goal that you're working towards. So good luck, everybody. All right, hang in there. Just another test. Remember, if you really wanted to, like, you could show up tomorrow and just like eat the AP test and walk out, and like you'd still be you, right? Not the best decision you could make. You're probably just better off sleeping in, but it's just a piece of paper or a bunch of pieces of paper. But please don't actually eat your test. All right. So here, region S, so y equals square root ln x. Now, one thing I want to point out here is that if it was just ln x, the domain is x greater than 0. However, natural log x is less than 0. So ln x is less than 0 on this space here. So that's like a subtle detail here that we have to be mindful of. And this was like an old school question, I think, from like the 1960s, maybe like 1967 or even 1973. So here we have to think carefully. When we throw a square root, now the negative stuff is no longer allowed. Like this is forbidden. Okay, so now the domain is x greater than or equal to 1. Okay, so that's just something here we have to be mindful of. Like I'm going to pretend we don't have a calculator for this and just say like, all right, this function is increasing and it's like born from x equals 1. So let's just say it looks, I don't know, something like that. I don't know what it looks like. E is definitely to the right. So the base of the solid is enclosed by the graph, x equals E, and the x-axis. So like these are the boundaries here. Okay, so this, and this. All right, and then they're taking this region, they're taking cross sections perpendicular to the x-axis and making them into squares. So I take one of those, I make it into a square. And the length is square root ln x. The infinitesimal like thickness here is dx. That's like, like the infinitesimal idea that it's like a small change. So the volume of this, it's a square, so all the sides are the same. So it'd be radical ln x times radical ln x, which is ln x, and then dx. Now, technically, this would be like a BC question today. If I had to do this the BC way, I would use integration by parts. So, I mean, I could show that real fast. For the interest of Calc AB, though, I'll just say that when we do antiderive, and we're going from 1 to E, I would just say, all right, trust me then that the volume is equal to the antiderivative is x ln x minus x. And then we're going from 1 to E. But Calc BC people, I would use by parts and say u is equal to ln x. Pen is possessed right now. So u is equal to ln x. So then du is 1 over x dx. And then dv is dx. See, in my integral, like this is my u term, and then this would be my dv term. Okay, so that's how I'm defining it. So then v would be the antiderivative of 1 is x. So then the antiderivative, I'll just write over here, is x ln x minus the integral of v du is x times 1 over x. And x times 1 over x is just 1 dx. So now, to antiderive this, I have x ln x minus the antiderivative of 1 is x, and then plus c. But it's a definite integral over here, so I don't write plus c over here. Okay, that would be if it was just the integral of ln x. Okay, that would be the antiderivative over here. So now the volume, I just plug in, and let's see, I should have gave myself more space for this. I'll have to write it over here. Okay, so we'll use that little space. So I'm going to simplify this over here. Is E ln E minus E, and then minus, I plug in 1, I get 1 natural log 1 minus 1. ln of 1 is 0. Natural log of E is 1. E minus E is also 0. So I get minus 1 is equal to 1. So wow, all of that equaled 1. It's pretty cool. All right. Don't sleep during the exam. I mean, unless you just need to sleep, then yeah, there's always next year. All right, so this one, I call it, I'm going to go on a side quest first. A side quest. So here I'm doing a u substitution. So I'm going to say u equals 1 plus x squared. So then du is equal to 2x dx. Now we could solve for dx, but once again, I personally like to solve for the leftovers. So you see how there's x dx left? That's what I'm solving for. So I would just multiply both sides by a half. And that's going to give us 1/2 du equals x dx. So now my antiderivative, I'll worry about the infinity later. So this is now BC. So yeah, BC questions. But AB people, you're, of course, welcome to stick around. So now I have 1/2. I'll section this off. I have 1/2. And I have x. Oh, James, thank you so much. I really appreciate that, James. Very kind of you. I hope you're doing okay, right? So, yeah, good luck to you all. But James, yeah, hello. So, shout out to James. So, 1/2, we have the 1/2 du is equal to x dx. So, I have 1/2 du is replacing x dx. And then I'm over 1 plus x squared squared is u squared. Please don't say like this. If you do, this is LOL. Don't say ln of u squared. Okay, a lot of people say that, and it's sad when they do, because it'll mess you up here. What you're going to say instead is this is 1/2 integral u to the negative 2 du. And now this, I could say is 1/2, not 1 over u, 1/2 u to the negative 2 plus 1 is negative 1. Divide by negative 1, you get a minus. Okay, and then plus c. If it were indefinite. Okay, and then this is negative 1/2 times 1 over 1 plus x squared. And then, yeah, plus c. So now back to the main quest. The integral from 1 to infinity. Oh, wow, William, thank you so much. This is so cool. I appreciate you all so much. Honestly, like I said it yesterday, like I'm not really like too much of a mushy guy, but like just thank you all. It's like so cool. You're all so awesome. It's yeah, I really can't believe like where the streams have gone, the channel just in general, and like knowing that 4,400 people stopped by to watch this, like to do some math with me, like that's really awesome. The high school I work at is like 3,100 kids, so this is like more people than my high school coming by to, learn some math. Like, thank you for being a part of this. This is like really, really just awesome. I hope you all get 5s tomorrow, for real. So now we have this, and the side quest, we could end it and say this is negative 1/2. So we did all of this just to anti-derive this. And we get negative 1/2 times 1 over 1 plus x squared. And we're going from 1 to infinity. So from here, what I'm going to do is I'm going to say this is negative 1/2 times, and I have 1 over 1 plus infinity squared is infinity. It's going to go to infinity. Remember, this, you will lose points in the FRQ, but this is multiple choice. Okay, don't do this for the FRQ. In the FRQ, you would say limit as b goes to infinity, integral 1 to b of, x over. But that's like, yeah, really tedious, especially if it's multiple choice. Like, please don't write that in the multiple choice. No one's going to read it. Minus, and then 1 over 1 plus 1 squared. So this part here goes to 0. And now I have negative 1/2 times negative 1/2 is equal to 1/4. Okay, so this works out to choice C. If you want to check your work, just write math 9 and plug in like even 50. It should get you to 1/4. Like if I did this right now, just math 9, and I go from like 1 to, I'll try 20 first. And I do x over 1 plus x squared squared. And let's see. Yeah, like we don't have, yeah, it's like, yeah, 1/4 is good. No, you don't need to show work. No one's going to look at it. You just guess everything right if you're really lucky. But I don't recommend that. Not a high probability of guessing them all. What would be the probability if you just like didn't even look at the questions? So that's like 1/4 to the power 45. So the probability of you guessing everything right is 8.0779 times 10 to the negative 28th power. Okay, so that's 0.000. So that's like 27 zeros. And then this. All right, that's really not a good, those are not good odds. So for sure, like learn the math. But yeah, they don't care about your work. It's just Scantron grades are multiple choice. But know how to show the work, because that's like definitely like what's gonna like help you get stuff right is if you know like how to get from. Oh, thank you, Maria. I appreciate that so much. Wow, look at this. Everyone's like, just I appreciate it. That was very kind. Thank you. Now I'm like, yeah, I have. Wow, look at this. Everything's adding up so nicely. Yeah, I appreciate you all like throwing tips my way. Like just you being here and lighting up the chat and all that though is like, it's like I said, it's nice knowing nearly close to 5,000 people stopping by while it's live. It's just like really cool. So, but thank you. So here's our derivative, and now dy dt is power rule 4t to the third. I'm just deriving this plus, and then I have 4t, and then minus 8. Okay, so that's the derivative of the top. And now the derivative of the bottom is dx dt. So I'm going to derive the x equation and get 3t squared minus 2t. So a vertical tangent, so we'll look at our friend slope guy. A vertical tangent represents slope guy's nose. So here, when we have a vertical tangent line, the slope is undefined. And if your slope is in the form of a fraction, that's when your denominator is 0. So we're going to just set the denominator 3t squared minus 2t equal to 0, and then solve for t. So we take out t, and we have 3t minus 2 equals 0. And for this, we have t equals 0 and t equals 2 over 3. Now, one thing we could do, because I mean, might as well just like look at some calculator stuff just for the sake of it, is if we were to go into parametric mode. So parametric, and I type this stuff in, I have t to the third, and then I have minus t squared minus 1, and I'm over t to the fourth plus 2t squared, and then minus 8t. And the points of time we had were 0 and 2/3. If I look at this, let's say I start at like -2, and now I press graph. And I'm going to press zoom 6 so that things go back to normal. So let's just see here. Did it actually window? Oh yeah, I'll go -2 like this. All right, and now I just punch in those times. Second trace value at 0, we are here. And it looks like, yeah, we have a vertical tangent at this point. So at 0, that seems fair. And if I do second trace value at 2/3, I'm on another part here where the slope is looking vertical. Okay, so this is definitely good. And, you know, if I wanted to, I could plug in 0 to dy dt and see, like, you know, y prime of 0 would just be equal to -8. And then y prime of 2/3. If I look here, plugging in 2/3, this would, yeah, I'm going to say here, this would give us something non-zero. So 0 and 2/3 are looking good, but I just like to draw these out and see, you know, what's happening. All right, polar. Which of the following gives the area enclosed by one loop of this polar curve? Now, if you have a calculator here, excellent. I'll show you how to do some calculator stuff. Otherwise, I'll show this without a calculator. So here, what I want to think about is this particular curve. If I plugged in theta equals 0, at theta equals 0, I have r equals 4 cosine 0. Cosine of 0 is 1, so I get this. So that tells me when I face theta equals 0 to go out a distance of 4. So I think of this as like my starting point. I'm going to start here. But notice when I start, I'm not starting at 0, 0. I'm starting at the end of the petal of the rose curve. So here, I just have to think about how many degrees do I have to go this way to get back to the origin. Now, if you have great eyesight, unlike me, you might be like, hey, I bet that's 30 degrees or pi over 6. But this is very risky to play that game, right? Unless you bring a magnifying glass, I don't recommend doing this. So then how do I know for sure it's pi over 6? Well, I just think about what I know about cosine. So this is the no calculator way. Cosine of pi over 2 is equal to 0. So what I'm going to do is I'm going to set our function here. I'm going to set 4 cosine 3 theta. I'm going to set that equal to 0, and that's going to be true when 3 theta, the argument or the inside of the cosine function, equals pi over 2. And you see, if we multiply both sides by 1/3 and solve for theta, theta equals pi over 6. But there's a lot of symmetry to this graph. Not only can I go positive pi over 6, I could also go negative pi over 6. And that's going to give me the entire petal that we're looking at over here. Now, the concept that I talked about the other days with polar area is the windshield wiper motion. That I'm just imagining that my windshield wiper is starting here and it's swiping this way to swipe that whole area that I shaded in green. Okay, so it's going from here all the way to here, and that's going to swipe this. But the windshield wiper shrinks as it swipes, or it grows, depending on the curve. So now I'm going to use our formula for polar area, which is 1/2 theta 1 theta 2 r squared d theta. And from here, now I just plug in, I'm going to have 1/2 integral from negative pi over 6 to pi over 6. And now r squared, I'm doing 4 times 4 is 16. Cosine times cosine is cosine squared, and then 3 theta. So I have 16 cosine squared 3 theta d theta. And from here, half of 16 is 8. So I scan carefully. Negative pi over 6, pi over 6. I'm going to get rid of the pi over 3s. And now negative pi over 6, pi over 6. These all almost match, but the coefficient now should be 8. Remember, I'll write the simplified one over here. It's negative pi over 6, pi over 6. The 8 I could just bring outside. And then I have cosine squared 3 theta, t theta. So I need an 8 on the outside. And it should be cosine squared, so choice E. Okay? Yeah, 16 cosine, but it's the formula for polar area is 1/2 integral theta 1 theta 2 r squared. All right? Question 17. Which of the following series diverge? This one, we could use, if I had to, I could use the limit comparison test. So the limit comparison test. So for the limit comparison test, here I'm thinking of just the leading terms. I'm thinking of 2 over k squared, but I'll even simplify it down to, I'm thinking of 1 over k squared. Okay, and this series converges. So this one here, which of the following series diverges? Not this one. This one is going to converge. And the reason I know is, once again, I'm just reminded of this series, and I know this one does, so this one does. Now, if I had to write something in the free response, I'm not going to say, oh, that one does, so does that one. That wouldn't get us credit. So I would say here, we're going to look at this series from k equals 3 to infinity of this. And what I'm going to do is I'm going to find the limit as n goes to infinity. So I'm pretending this is FRQ. In multiple choice, I'm not doing this, but FRQ I am. 2 over k squared plus 1 over 1 over k squared. This limit is going to simplify to n goes to infinity, and I'm going to have 2k squared over k squared plus 1. This limit equals 2, which is positive and finite. So by the limit comparison test, since sigma k equals 3 to infinity of 1 over k squared converges, and how do we know it converges? Because it's a p-series. It's a p-series where the power is 2, which is greater than 1. Now I could say, by the limit comparison test, the original series converges as well. Right, that would be if it was FRQ. It's a lot to write. Multiple choice, please don't write that. No one's reading it. All right. This is a geometric series. It's in the form of r to the k, and the absolute value of 6 over 7 is less than 1, so this series will converge. If I want to find what it converges to, it's equal to the first term, which we could find by looking at where the series starts. It starts at k equals 1. So that's 6 over 7 divided by r is 6 over 7. So this would be 6 over 7 divided by 7 over 7 minus 6 over 7 is 1 over 7. So this would actually converge to 6. Okay, so this would converge to 6. Cool. So that one converges. And this one converges, wow, they all converge. This one converges by the alternating series test. Okay. This one starts out, this is the same thing as 1 over 2. If I plug in 2, negative 1 squared is 1 over denominator 2, and then minus 1/3 plus 1/4 minus 1/5. So this converges because it's an alternating series and the terms are decreasing in magnitude to 0. Okay, it's not enough to just say they're decreasing in magnitude, they're decreasing in magnitude to 0. If I had to write that out, so now I'll erase this, I would say, like, let b sub k equal 1 over k. Then I would comment that 1 over k is a decreasing, so this is a decreasing sequence when k is greater than or equal to 2, and the limit as k goes to infinity of 1 over k is 0. So this basically says like it's decreasing in magnitude to 0. So then I could say here, like, therefore, by the alternating series test, so by AST, the series converges. Okay, I would start off too saying, hey, this series alternates. Okay, cool. All right. So let's see. So moving on. All right. Next up, we have, oh, this is a nice one. So we have from unit 10, we have this series. It's alternating because they're saying a sub n is greater than 0, but the negative 1 to the n makes it alternate. And next we have, which of the following conditions guarantees that the series converges? So this one, just because the limit of the nth term is 0, does not guarantee the series converges. The alternating series test, we also need a sub n to be decreasing. Okay, so a sub n has to, like, we need, so for this, we need a sub n to be a decreasing sequence. If they don't tell us that it's decreasing, then we can't use the alternating series test. So this one's no good. This one is good. This is the ratio test. Okay, because when we do the limit as n goes to infinity of, and let me just clean this up. So when we do the limit as n goes to infinity of this, and they told us a sub n is greater than 0, the absolute value would honestly just get rid of this. So that's why here we would just get the limit as n goes to infinity of a sub n plus 1 over a sub n. And if this is less than 1, then by the ratio test, our series converges. Okay, so that's the ratio test. This one says a sub n plus 1 is less than a sub n. This, honestly, like, this one is wrong, but if we combined like this and this together, then I could say the series converges. If the terms of the sequence are decreasing, like if this is a like this says in math language, what I have over here, like this that I'll highlight in yellow. So this and this say the same thing, that this is a decreasing sequence. I need A and C to be true for the series to converge. And now this one, if integral f of x dx converges, where f of n equals a sub n for all n, the problem is the integral test, you need 3 things. F of x has to be continuous, positive, and decreasing. Okay, on 0 infinity. Which we can't guarantee that. We can guarantee that it's positive, but we don't know if a sub n equals f of n is continuous and decreasing. So that's why this one's out, and it's got to be B. Yeah, so continuous, positive, decreasing. For AST, just going to cut my losses and move on. Yeah, I mean, for AST, it's not, it takes a second to get good at, but it's not the worst. I mean, I don't know. It can be, yeah, I think for some people it's definitely a little tricky. But when I have something like this, I really just have to isolate and say, like, all right, B sub n is 1 over n. And let's say this is like n equals, I don't know, 2 to infinity. And then I just have to write 2 things. I say that 1 over n is a decreasing sequence. And the limit isn't bad. And the limit as n goes to infinity of 1 over n equals 0. And I would say, like, this is like, yeah, so this is like an alternating series. Just comment this is an alternating series. So then I'll say therefore. So therefore, 3 dots, or the 3 dots means therefore, by the alternating series test, sigma n equals 2 to infinity of -1 to the n over n converges. Okay. One thing that I think is useful is this is not an actual rule, but I like to name it this: the alternating p-series test. That when you have something like this, like -1 to the n over n to the p, if p is greater than 0, then the series converges. But this is only for alternating, okay? Don't use this for everything. This is just for alternating series. Okay, so if I have an alternating series and my power on bottom is greater than 0, I have like -1 to the n over np, we have convergence, and when we're less than or equal to 0, we have divergence. The regular p-series test, remember, is, so for p-series, we have sigma 1 over n to the p. If p is greater than 1, we have convergence. Okay, the series converges. Less than or equal to 1, we have divergence. Okay, but if it's alternating, it's more forgiving. We just have to be greater than 0, right? Cool. So this one, the coefficient of x to the 6 and the Taylor expansion of this. So there's 3 series you really have to know: sine, cosine, e to the x. I'll add a 4th one in. You also need to know 1 over 1 minus x. Like that 1 over 1 minus x is the integral from n equals 0 to infinity of x to the n power, provided that like this converges. Okay, like it's not like 5 to the n or something crazy. So if I have sine x, that's x minus x to the 3rd over 3 factorial plus x to the 5 over 5 factorial minus dot, dot, dot. So when I want to build up f of x, which is equal to sine of x squared, I'm going to write the series for sine x, but without the x's. I'm going to leave it blank. And then it's a game of algebra. So now I plug in x squared. And I have x squared minus x to the 6 over 3 factorial plus x to the 2nd to the 5th. I do 2 times 5 is 10 over 5 factorial minus dot, dot, dot. All right, now I'll erase this. So here, what is the coefficient they're asking of the x to the 6th term? So the x to the 6th term is over here. So if I focus just on that piece, that's -1 over 3 factorial. Does not mean shout the number 3 at me. That means 3 times 2 times 1, which is 6. Okay, so this is -1 over 6, x to the 6. So the coefficient is -1/6. Okay, last question. All right, what is the interval of convergence? Something like this, you can use the ratio test. You could also just plug in the answer choices, and hope for the best. So the plugging in the answer choices method, it does work, but you just have to be, really, really savvy and really know what's going on here. Like, I mentally group this and this together, and then I mentally group these terms together, because these are the ones that are exponential, and then the yellow stuff is power terms. So here, if I'm just like kind of going through this casually, I know that this will converge as long as the exponential stuff, the absolute value of it, is less than 1. So I'm looking at x minus 4 to the n over 3 to the n. And I'm looking at that and saying, okay, if my denominator is greater than my numerator, I'm okay. So I look at something like, all right, let's say I plugged in something like 6. I plug in 6, which is between here and here. 6 minus 4 is 2. So like 2 to the n over 3 to the n is 2/3 to the n. And I'm like, all right, this will converge. So this is just like mental math. So I'm like, all right, these are out because 6 is outside of this and 6 works. So this is just by like, I don't feel like doing the ratio test. I'm just going to like common sense this. But now if I plug in 7, 7 is no good. 7 is no good because if I plug in 7, I have 3 to the n over 3 to the n cancels. And now I have left over, I have n over n, which goes to 1. So we're not going to have convergence at 7. So my educated guess is C. But now I'm going to do the ratio test and see. That's like a savvy way of getting to the answer if you don't feel like doing the ratio test. But the ratio test is safe. So we're doing, remember, it was a sub n plus 1. I'll write it over here. Over a sub n. So I have absolute value of -1 to the n plus 1. So I'm just going to add 1 to all of those. So when I do n plus 1 plus 2, I'm going to get n plus 3. Over, I have n plus 1. And then times 3 to the n plus 1. And then I have times x minus 4 to the n plus 1. And when I divide by the original, okay, so I'm dividing by, let's call this whole mess a sub n. Dividing by a sub n, just multiply by the reciprocal. Okay, so I'm going to multiply by, we're going to have n times 3 to the n. And then on bottom, I have -1 to the n times n plus 2 times x minus 4 to the n. Okay, so some messy algebra here. Now, one thing to point out, the absolute value is going to wipe out the -1s to the n and n plus 1. So this I could just chop. And now here, 3 to the n, I'm comparing these. 3 to the n and 3 to the n plus 1. I'm also comparing these. X minus 4 to the n plus 1 versus x minus 4 to the n. So this cancels out, and this we're left with the power of 1 because n plus 1 is 1 more than n. And then here I have x minus 4 to the n is gone, and I'm left with the power of 1. So now I have the limit as n goes to infinity of absolute value. And now I'm going to write we have the x minus 4 is left. On bottom, we have 3 to the first. So I'm going to put those two together. And now we're left with times n plus 3 times n over n plus 1 times n plus 2. Okay, now the thing to pay attention to is that we're going to get like an n squared on top and an n squared on bottom. And it's the limit as n goes to infinity. So this is the only thing affected by the limit. That's going to go to 1 because the leading terms match. They have like the same power and same coefficient. So this is just going to be 1 times this. So I have the absolute value of x minus 4 over the absolute value of 3 is 3. And we need this to be less than 1. So then I would have, if I multiply both sides by 3, the absolute value of x minus 4 is less than 3. So now this tells me my center, and this is my radius of convergence. So the concept then, if my center is at 4, and I have a radius of 3, if I do 4 plus 3, I get 7. If I do 4 minus 3, I get 1. So you see, like, C is looking good. But I already showed before that I plugged in 7 and showed that it wasn't going to work out. So if I do that again, if I plug in 7, like more formally, we could see that's the only difference between them. I plug in 7, and I'm just going to write the sigma. We have -1 to the n. We have n plus 2 over n times 3 to the n, and we have x minus 4 to the n. But if I plug in 7, I'm going to get 3 to the n. which is going to wipe this out. And then by the nth term test, you see everything left here. The limit as n goes to infinity of this is not 0. So we have the series will diverge here, this divergence. So definitely C. And that is it. All right, that is the last multiple choice. 2 hours and 40 minutes. Yeah, I said I was going to like try to just do an hour and a half, but I don't know. I just felt bad. I wanted to stick around and get you all as much practice as we could. All right, so at this point, I am just going to say, good night and good luck to all of you. Remember, it's normal to be nervous. That means you care. But I'm just going to say, try to convert that anxious, nervous energy into test-taking energy. It's very like Customato was old boxing trainer, and he said like, oh yeah, fear is kind of like fire. Oh, you'll like this one. Fear is kind of like fire. You could either cook with it or it could burn down your whole house. So here I would just say, if you're nervous, like use it at the test, like use that energy. Okay. And just focus on putting the best math down on paper that you can and see what, see where it goes. The rest is just like, up to chance. Okay. So good luck, everybody. I hope tomorrow is your good day. But either way, I'm proud of you for being on here with me, studying the night before your test and, putting in that effort. So good luck. And it's been fun. All right. Take care, everybody.